and welcome to Module 9. In today's video, we're going to be covering the topic of enthalpy. Enthalpy, denoted by H, is the measurement of energy in a thermodynamic system. The change in enthalpy, denoted by delta H, is the energy required to either form or break a bond. Now, how do we measure the change in enthalpy? Well, we take into account something known as the heat of formation, or the amount of heat released or absorbed when 1 mole of a substance is formed from its constituent elements. Take into consideration the formation of water. Here we see that we can only form 1 mole of water, in this case since it's heat of formation, and the elements that make up water are going to be hydrogen gas and oxygen gas, right? The diatomic oxygen. And in this case, we see here that this reaction involves elements in their natural state, right? We have hydrogen gas, oxygen gas, and liquid water, right? And so here we see that 1 mole of water is going to be formed by 1 mole of hydrogen gas, but half a mole of oxygen gas, since we only have 1 oxygen on the product side. This reaction is known as the standard heat of formation. It is standard since the elements that make this substance are in their natural state, or at room temperature and sea level pressure, or at 25 degrees Celsius and 1 atmospheric pressure. Take note that an element in its natural state has a standard heat of formation of 0 kilojoules per mole. That's the amount of energy that elements in their natural state have, right? So hydrogen gas is going to have 0 kilojoules per mole, and oxygen gas is also going to have 0 kilojoules per mole. Now let's take a look at how to calculate the standard heat formation in a given reaction. We see that we're going to be using the direct method of knowing how to find the enthalpy change in a reaction. And this is given by this equation. The standard heat of a reaction is going to equal the sum of the heat of formations of the products minus the total sum of the enthalpy change, or the heat of formations of the reactants. Right? And so in this case, we see, for example, that the standard heat of formation can equal the standard heat of the reaction. Why is that so? Because here we see that hydrogen gas and oxygen gas are in their elemental natural state, and they both have a heat of formation of 0. While on the other hand, water is going to have a heat of formation of around negative 277 kilojoules per mole. And so when we take a look at how is it possible that the heat of formation of water is going to be the same as the heat of formation of the reaction, well, we plug it into this formula, right? And here we see that we're going to plug in the sum of the heat of formations of the products. Take note that N stands for mole. So when we write this down, we're going to be writing this equation as follows, right? We want to write the brackets since we want everything that's inside of it. We have 1 mole of water times the negative 277, which is the heat of formation for water, right? And so that's all we have for the products. There's not really anything we can add to that. But then we subtract it by the sum of those in the reactants. We see that we're going to have 1 times the 1 mole of hydrogen plus half a mole of the heat of formation of oxygen, right? And in this case, the heat of formation for both of them, since they're in their natural state, is going to be 0. And so here we basically have that the standard heat of the reaction is the standard heat of the reaction is going to equal what is negative 277 minus 0 practically. So it's just going to equal this negative 277, right? Now, let's actually take a look at a proper example of how this can be used to find the total heat of reaction given other substances, right? So here we have our first question. We have that we have the ethanol, oxygen gas, carbon dioxide, and water, and we want to find out what the total enthalpy change is given the reaction of 1 mole of ethanol, right? And so first things first, we want to balance. We always want to start off by balancing this equation. And given that this is a combustion reaction, given that we have carbon dioxide and water as our products, we want to start off with carbon first as opposed to the other elements. And we'll see right now in a second. So first of all, we see that we have 2 carbons on the left side, and we have 1 on the right side, so we can put a 2 here as the coefficient, and so that now becomes balanced. Next, we can work with hydrogen. We see that we have 6 hydrogens over here. We have this 5 and this 1, and we only have 2 on this side, so we can divide that and get a whole number, right? We can divide 6 divided by 2, and that will give us 3. Now we can finally work with oxygen. Why do we leave oxygen till the end? Well, we can see that it's going to be in its natural state, so it won't really affect the standard heat of the reaction, given that the standard heat of formation for oxygen is going to be 0. So we're not done balancing yet. We know that here we're going to have 1 oxygen on the ethanol and 2 oxygens in the oxygen gas. We see that we have 4 oxygens in CO2, right, because we have 2 moles of CO2. We see that we're going to have 3 moles of oxygen, since we have 3 moles of the water molecule. And so this is 4 plus 3 is going to give us 7. And on this side, we have 1 plus something else. It has to give us 7, right? And a multiple of 2, just like how we divided 6 by 2, we can also multiply 2 by 3 to get 6, right? And so 2 by 3 is going to give us our magical little 6 here that is going to equal the 7, right? And so now we finally have our balance formula, right? Oops, I accidentally deleted that. We know it's going to be liquid water. Now let's look at how to find the standard heat of the reaction. Given that the standard heat of formation for ethanol is negative 268, the standard heat of formation for oxygen is 0, the standard heat of formation for carbon dioxide is negative 144, and the standard heat of formation of water is negative 268, right? Or 277. Apologize. 277. And so we look again at the standard heat of formation reaction formula, right? We have that standard heat of reaction is going to equal the sum of the heat of formations of the products minus that of the reactants, right? And so we begin by plugging and plotting everything down, everything that we do have. So we see here that in the product side, we're going to have carbon dioxide and water. And so here we want to take note of this lovely N, right? The amount of moles that we have. So in this case, we're going to be multiplying 2, right? Because we have 2 moles of carbon dioxide times the negative 144 that we have as the enthalpy change of carbon dioxide, and that's going to be the sum of the products, right? So we want to add that to the enthalpy change in water. And so in this case, we see that we have 3 moles of water, and that's going to be that times the heat of formation of water, which is negative 277. Right? And so this is going to be the total heat of formation of the product side. And so what we want to eventually do with this number is subtract it by the sum of the reactants. And so since I don't have enough space here, I'm going to write it down beneath it. So this is going to be minus, right? Minus this reaction on top. We're going to have the enthalpy, the heat of formation change in the reactants. And so first we see that we're going to have 1 mole of ethanol times the negative 268 kilojoules per mole. And that's going to be added to the 3 moles of oxygen. But in this case, we see that the heat of formation is going to be 0. So we don't really have to take into account this oxygen here, but it is nice to write down everything just in case of errors, right? So now let's try to simplify this problem a little more, right? So now let's see. For 2 times negative 144, we're going to get negative 288, right? Negative 288, and then 3 times negative 277 is going to give us a negative 831. And so this plus sign here is going to turn into a negative or a minus sign. And when we subtract these two numbers, we're going to get a total of negative 1,119, right? And so this, we want to subtract it by that of the reactants. And in the reactants, we see that we only have that negative 268 to worry about. There's going to be minus, right? It's going to be minus the reactants, but in this case, because there's 2 minus symbols of the negative 268, this is going to become a positive. And so we're going to add the 268 to this number. And so now we see that the standard heat of formation for the total reaction is actually going to equal the standard heat of formation of the reaction is going to equal a total of negative 851 kilojoules per mole. And so I hope you guys were able to understand a little bit more about the topic of enthalpy. And on the next video, we're going to cover Hess's law, or the indirect method of changing the heat of formation around and being able to formulate the overall heat of formation of a given reaction. Thank you guys, and I'll see you guys soon.